Welcome to today's Explainer. Today, we're unpacking an absolutely fascinating piece of science history. We're going to look at how one carefully constructed physical machine actually managed to prove a completely mind-bending quantum theory. If you enjoy getting into the nuts and bolts of how theoretical physics becomes proven fact, well, you're definitely in the right place. We're going to break down the mechanics, the math, and the massive paradigm shift this core model triggered. But first, we really have to start with the seemingly impossible question at the very heart of this whole mystery. Can a solid particle act like a rippling wave? I mean, really think about that for a second. If you throw a baseball, it travels like a solid object, right? But down in the microscopic realm, scientists started to wonder if a fundamental particle, specifically an electron, could behave like a wave and actually produce things like diffraction and interference. It sounds totally contradictory, doesn't it? All right, let's dive into this by looking at the stark contrast between what we thought we knew and what was being hypothesized. Before this core experiment even took place, classical physics had a very, very rigid view. Electrons were considered strictly particles, little solid spheres of negative charge. But there was this radical new hypothesis emerging. The idea was, if an electron truly has a wave nature, then it shouldn't just bounce off things. It should produce diffraction and interference patterns exactly like light does. Now, to test a hypothesis this wild, you can't just do math on a chalkboard. You literally have to build a physical machine. And that brings us to the minds behind the experiment, Clinton Davisson and his colleague Lester Germer. They set out to construct a core experimental model that could definitively answer this big question. They needed a way to shoot electrons at a target and precisely measure how those electrons bounced, or rather, rippled away. The stakes were incredibly high here. The results from their machine would either confirm classical physics or just completely rewrite the rulebook of the universe. So, let's look at the high-level anatomy of their machine. The true beauty of their core model lies in its structured simplicity. It really breaks down into 3 clear steps. Step 1, the electron gun accelerates electrons using a known voltage. Keep in mind here, a higher voltage means faster electrons. Step 2, those accelerated electrons strike a target, specifically a nickel crystal. And finally, step 3, a detector measures the intensity of the scattered electrons at different angles. It's a beautifully logical flow, right? Fire, strike, and measure. Okay, now let's map those 3 steps directly onto the actual schematic of the Davisson-Germer apparatus. Over on the left, we've got the heated filament that is our electron source. Those electrons are then pulled forward by the accelerating anode to create our precise beam. And notice how all of this is housed inside a vacuum chamber that's absolutely crucial to ensure the electrons don't collide with any stray air molecules. Finally, the beam hits the green nickel target on the right, and a movable detector swoops in an arc to capture those scattered electrons. Now, actually visualizing the unseen physics happening inside that vacuum chamber is just fascinating. The electron gun fires that bright blue, precise beam directly into the nickel crystal lattice. But watch what happens after the strike. Instead of a chaotic spray of particles, the beam scatters in very specific directions toward that detector arc on the right. This core model was specifically designed to capture that exact intensity pattern, basically mapping out where the electrons went after hitting the atomic structure of the nickel. To really understand why the nickel target was chosen in the first place, we have to zoom way in on the microscopic mechanics of the crystal itself. Look at those yellow atoms, perfectly aligned in regular layers. When the electron beam, represented here by the red arrows, strikes the sample, it penetrates these different layers. And because the atoms are arranged in such a beautifully regular repetitive pattern, they actually act as a natural microscopic diffraction grating for the incoming electrons. The physical structure of the crystal is the crucial mechanism that essentially forces the wave behavior to reveal itself. And that brings us to the startling experimental results. If electrons were just solid little spheres, they would have scattered off that nickel lattice completely randomly, kind of like dropping a handful of marbles onto a bumpy floor. But that is definitely not what the detector measured. Instead, it revealed sharp intensity peaks. The electrons formed distinct concentric diffraction rings. They were behaving exactly as waves do during diffraction. The machine had successfully captured the physical footprint of an electron acting as a rippling wave. No way, right? So, with the physical evidence secured, the next step was to connect these physical results back to the theoretical model. And this relies on a famous physics principle proposed by Louis de Broglie. Lambda equals h over p. It's elegantly simple, honestly. Lambda is the wavelength of the particle. The h is Planck's constant, which is a fundamental number in quantum mechanics, and p is momentum. This equation mathematically predicted that you could calculate the exact wavelength of a particle based purely on its momentum. Let's walk through this relationship and see how it builds our understanding of the math. Remember how step 1 of the machine used voltage to accelerate the electrons? Well, a faster electron has a higher momentum. And according to the equation, because momentum is the denominator, a higher momentum results in a smaller wavelength. Conversely, a slower electron has lower momentum, which gives you a larger wavelength. By simply adjusting the dial on the initial voltage, Davisson and Germer could directly manipulate and test the wavelength of the electrons. So here is the absolute crucial takeaway. This core experimental model didn't just produce a neat visual trick. When Davisson and Germer measured those sharp intensity peaks and calculated the angles of the diffraction pattern, the numbers perfectly matched the wavelength predicted by de Broglie's equation. I mean, perfectly. The physical measurements generated by the machine definitively and mathematically proved the theoretical math. It was a flawless marriage of hypothesis and experimental confirmation. Because of this flawless alignment between theory and experiment, science was forever changed. It gave rise to the ultimate paradigm shift, wave-particle duality. This is literally one of the foundational cornerstones of modern quantum physics. After this experiment, we just couldn't look at the universe the same way anymore. Electrons aren't just particles. They inherently possess both wave and particle characteristics, depending entirely on how you measure them. It's a fundamental truth of nature, proven by one meticulously designed core model. And this brilliantly illustrates why such an abstract theory actually matters in our everyday reality. The Davisson-Germer experiment helped launch the era of quantum mechanics. And today, we use that exact same wave nature of electrons in modern technology. Think about the electron microscope. Because electron wavelengths can be manipulated to be thousands of times smaller than light waves, these microscopes allow scientists to resolve details that ordinary light microscopes simply cannot see. We are using this wave-particle duality today to study atoms, viruses, and advanced materials with extraordinary, life-saving precision. Which leaves us with a fascinating final thought for this explainer. If a simple machine firing electrons at a piece of nickel could reveal an invisible quantum reality that completely changed modern technology, well, it really begs the question, what other invisible quantum rules are quietly powering the technology we use every single day? Understanding these core models is absolutely the key to unlocking the universe. Thank you so much for joining me to explore this incredible scientific breakthrough. Stay curious, keep learning, and I'll catch you in the next explainer.